Okay, so today we are just covering properties of rational functions because we are going to start graphing rational functions in the next section. So today we'll cover domain of a rational function, and we'll cover something called asymptotes. There are vertical asymptotes, horizontal asymptotes, and possibly oblique or power asymptotes of a rational function. So we will touch on all of these today. Let's start off with the first page. Should be a nice refresher for you guys. We are going to start off by finding the domain of a rational function. And remember, a rational function is in the form of r of x equals p of x over q of x, where the denominator q of x can equal 0, and p and q are polynomial functions. So rational is just fancy for fraction. So for number 1, we're given r of x equals 2x squared minus 4 over x plus 5. So remember, to find the domain of a rational function, you would take the denominator and set it equal to the number, the number that can never, ever be in your denominator. And what number is that?
-5.
Well, we can't plug -5 in because it'll give
0.
us what number?
Okay, yeah.
0. There you go. Then you solve for x, and you'll get x equals -5, which can't happen because we'll get a 0 in our denominator. Okay, so that's our domain. X can equal -5. We can even do the interval notation, -∞ to -5, and union -5 to infinity. All right. Everybody good with that? All right. Like I said, should be a refresher. Hopefully by now we know how to find the domain of rational functions. Okay, let's do it again. Number 2, 1 over x squared minus 4. So for our domain, we take the denominator, we set it equal to 0. And here you can use the square root method if you'd like. Move that 4 over. And if you square root both sides, we'll get x cannot equal what two numbers?
Two and -2.
Good. 2 and -2. All right. And again, good to practice interval notation. -∞ to -2. Union -2 to 2. Union 2 to infinity. All right. Okay. 3, same thing. Get that domain. Take your denominator and set it equal to 0. Okay. So here you'll get x squared equals -1. And what's wrong with this one? I guess not what's wrong with it, but what happens if we try to solve for x? What type of numbers do we get?
You get imaginary numbers.
You get
for an answer.
imaginary numbers. So if we get imaginary numbers, what does that tell us about the domain? We can't say x cannot equal plus or minus I, because what this is saying is that imaginary numbers are the only numbers that will make this denominator 0. So what does that mean for our domain? What numbers could I use for my domain? Think about it, right? If only imaginary numbers make this function undefined, then what are the numbers I could use for this domain?
real numbers?
That's it. All real numbers. So our domain ends up being just negative infinity to infinity. That's it. So if imaginary numbers are the only numbers that make your function undefined, then this means that the domain is the set of all real numbers. Does that make sense? All right. Okay. Third one, here's our domain. We take the denominator, set it equal to 0, and solve for x. Easy enough, our domain is x cannot equal what number?
One.
1. There you go. X can equal 1. There's our domain. It's good to practice interval notation. So negative infinity to 1, union 1 to infinity. But before I move on from this problem, go ahead and look at the numerator of this function. Can you simplify this function? What is x squared minus 1?
One or 0?
Wait, what?
No.
X
hang
squared
on.
minus x
One.
squared minus 1. I'm talking about simplifying. Could you factor it?
Oh, x minus 1 times x minus 1.
There you go.
Or x minus 1 times x plus 1.
Either way you want to say x plus 1 times x minus 1. Whoops. Or x plus 1 times x minus 1. And now what do you notice?
X minus 1 cancel out.
Cancel out. And we're left with the new function of x plus 1. Okay. Does this function still follow the original domain?
It
I mean, it should, right? But it doesn't. But it does.
It does. Good.
It gets grandfathered in or whatever.
Hey, whatever makes sense. I like that. So when you take a rational function and you reduce it, no matter what, that reduced function still follows the original domain. So when we deal with rational functions, whenever you cancel out a term in the denominator, it creates something called a hole in the graph, right? So once you cancel it out, x equals 1 now becomes a hole in the graph. So if I were to graph this function, x plus 1, it would look something like this at 1. So we cancel out a piece of the function, therefore it creates a hole in the graph, and whatever the reduced function is, it still abides by the original domain. So this means that the new reduced function of x plus 1 still cannot exist at the x value of 1. Okay. So just have to show that because we may run into something like that in these notes or in the next notes when we're graphing actual rational functions. Okay, so that's finding domain. Any questions on this page? All right. All right then. Next up is the definition of asymptotes. So asymptotes are going to be a line that our function approaches. And depending on the asymptote, when our function approaches it, our function can either head towards infinity or negative infinity. Or depending on the asymptote, our function can actually approach an actual number other than infinity or infinity. So by definition, let R denote a rational function. If x approaches negative infinity, or as x approaches positive infinity, the values of R of x or the values of y will approach some fixed number L. Then this line is called a horizontal asymptote of the graph of R. So I have a picture of a horizontal asymptote below. So here's our graph, and it says as x approaches infinity, so if we're headed to the right, this means that as x approaches infinity, this graph starts to approach some line known as y equals L. So as x gets larger and larger, y gets closer and closer and closer and closer to this line, but may never touch it. So that is the definition of an asymptote, and that's the definition of a horizontal asymptote, which I have another one down here. It says, in the form of y equals L, this describes the end behavior of the graph as x approaches positive or negative infinity, and we get closer and closer to the line, and the graph of a function may intersect a horizontal asymptote. So just to draw more pictures of this, why not? Let's say I had a graph, and let's say my function did something. First off, I'll draw a horizontal asymptote here. We'll call this y equals L. And let's say my graph looks like this. So as x heads towards infinity, this graph would come up and get closer and closer and closer to that line, but it may never touch it. Okay, and the same would go for x going to negative infinity. Let's say x was going to negative infinity, and I had a graph coming down this way. We would get closer and closer and closer, but possibly never touch it. So that would be as x approaches negative infinity. Okay, so that's a horizontal asymptote. The next definition would be for a vertical asymptote. If x approaches some number c, the values of y will either approach infinity or negative infinity. This means that the line x equals c is a vertical asymptote of our function. Okay. So again, I have a picture of vertical asymptote down below. So this says as x starts to approach some number c, so as x starts to approach some number c, we see that the graph could head towards negative infinity, or the graph could even head towards positive infinity. So this is a vertical asymptote. And when we are graphing rational functions, vertical asymptotes come from the denominator. They come from your domain. So vertical asymptotes can never, ever be crossed. You can never intersect them or cross a vertical asymptote because they come from your domain. They are we could say a consequence of your domain. So let's say I have a vertical asymptote over here. Let's say this is x equals c. And as we approach c, I have a tail that will approach it and go up towards infinity. That's as I approach c from the left. And if I approach c from the right, I could have a tail go down to negative infinity. Okay. So that's a vertical asymptote. And then one of the last asymptotes is called an oblique asymptote. And this says that as x approaches positive or negative infinity, the value of a rational function, the y values, will approach a linear expression in the form of y equals ax plus b or y equals mx plus b. And this line is called a linear or oblique asymptote. And the graph of a function may intersect an oblique asymptote. So the picture down below is just perfect. So The red line is my oblique or linear asymptote. And we see that as our function approaches positive or negative infinity, we get closer to that linear or oblique asymptote, but may never touch it. So same thing over here. Okay, so horizontal and obliques, you can possibly intersect. Vertical asymptotes, you can never intersect. So that's the definition of asymptotes. Any questions on this page? All the definition, breathe it in. Okay. All right. So remember that, what was it? X-intercepts, zeros, roots, they had multiplicities. Well, vertical asymptotes have multiplicities as well. So for number one, it says if the multiplicity of the zero that gives rise to a vertical asymptote is odd, then the graph will approach positive infinity on one side and negative infinity on the other side. So for number one, we have the function 1 over x minus 2. If we solve for x on this function, you'll just get x equals 2, which only shows up once. This means that this asymptote, this vertical asymptote, would have an odd multiplicity. So when you graph the function, one tail will head towards negative infinity, and another tail will head towards positive infinity. So that is multiplicities for vertical asymptotes. And the one on the right is same thing, same function, except the function is negative. So if you think about transformations, this negative would just flip your tails or your y values over the x-axis. And if you solve for x, you'd still get x equal to 2, where is an odd multiplicity, and one tail would head towards infinity, another tail would head towards negative infinity. So asymptotes with an odd multiplicity will have tails of a function going to infinity and negative infinity. This means that for asymptotes that have an even multiplicity, this means that the tails will both go to positive infinity or both go to negative infinity. So for the first picture, we have 1 over x minus 2 squared, which means if you solve for x on this function, you'd get x equals 2, which means it would have a multiplicity of 2, an even multiplicity, and therefore both tails would head towards infinity. And then in the second picture, we have the same function, but negative. So our tails flip down. If you solve for x, you'd still get x equals 2, where they would all have even multiplicity, and your tails would both head towards negative infinity. Okay. So vertical asymptotes with odd multiplicity will head towards infinity and negative infinity, and vertical asymptotes with even multiplicity will either head towards positive infinity or both will head towards negative infinity. More asymptote definition. Everybody good? Surviving? All right. So what we want to do on this next page is locate vertical asymptotes. So to keep it really, really simple, to find a vertical asymptote, all you have to do is find the domain of the rational function. And if you find the domain, you have your vertical asymptotes. That's it. So for number one, you have x plus 3 over x minus 1. What is the domain of this function? x can't equal 1, which means, again, if you have your domain, you have your vertical asymptote. So this means that my vertical asymptote is going to be the line x equals 1. They go hand in hand. Nothing easier than that. Okay. And x equals 1 is the graph of a vertical line. So that's all we're going to do is plot it on here. I'll say here's 0, here's 1. And this would be my vertical asymptote at x equals 1. All right. So if you have your domain, you have your vertical asymptotes. 2, x over x squared minus 4. What's my domain for this function?
Two or -2.
Good. Which means, what are my vertical asymptotes?
-2 and 2.
There you go. -2 and 2. And just draw them out. So 0, say this is 2, and there's -2, and then that's x equals 2. And x equals -2. Okay. Perfect. Next one. X squared over x squared plus 1. What is my domain for this function?
All real numbers.
All real numbers, which means that if it's all real numbers, do we have any vertical asymptotes?
No.
No. None. Okay. That means we don't draw anything. And then 4. Oh boy. My domain. You take x squared plus 4x minus 21 equal to 0. What are 2 factors of 21 that will make 4?
7 and -3.
7 and -3. Good. And this means that, no, stop it. There we go. There we go. This means you get x can't equal -7 and x can't equal 3. So this means that your vertical asymptotes would be x equals -7 and x equals 3. Okay, but look at the numerator again. Can you simplify this rational function? X squared minus 9 is what?
Three. X equals 3.
Well,
Oh,
you
okay,
want
I
to
guess X plus 3,
factor
X
it.
minus 3.
There you go. X plus 3, X minus 3 over that factored denominator of x plus 7 times x minus 3. And what happens next?
X minus 3's cancel out.
Cancel out. And we get x plus 3 over x plus 7. Okay. Which means that, which term did we eliminate out of the denominator?
The 3.
The x minus 3, right? So this means that if we eliminate that term, this x equals 3 is no longer a vertical asymptote. This x equals 3 becomes a hole in the graph. So whenever you're finding your vertical asymptotes, or whenever we are dealing with a rational function in general, the first thing you want to do is find the domain. You find domain first, and then you simplify. So always find domain first, and then simplify. Okay. Well, we were supposed to graph these, so we're 7. 0, 1, 2, 3, 4, 5, 6, 7. And then there's that. So this would be x equals -7. And then for the whole, you would plug that 3 in to this function to find the exact location of where to plot the hole on the graph. And you'd get 6 over 10, or what would that be? 3/5. So 0.6. So you'd probably have at 3, probably have a hole in the graph around there. Okay. So that is finding vertical asymptotes. So definitely simple to remember. If you have your domain, you have your vertical asymptotes. Okay. And then a common mistake students make is when they are finding their vertical asymptotes, they'll say, oh yeah, vertical asymptote is 2. That means nothing. 2 is a number. X equals 2 is a line. So don't make that mistake. My math lab will even count you off if you do that. So remember, x equals 2 is an actual line. 2 is just a number. Don't make that mistake. All right. That's vertical asymptotes. And now we have horizontal asymptotes. Okay. So first thing to talk about is a proper rational function. It's the same thing as a proper fraction. To be a proper fraction, that means the numerator has to be smaller than the denominator. To be a proper rational function, this means that the degree of the numerator has to be smaller than the degree of the denominator. If you do not have a proper rational function, then you will have to fix it by long division. So that is information about a proper rational function. Okay. So finding a horizontal asymptote. There are 4 rules to finding a horizontal asymptote. So by definition, let f of x be a rational function, a proper rational function. Rule number 1 says if the degree of the numerator is smaller than the degree of the denominator, then the horizontal asymptote is going to be the equation y equals 0. That's for number 1. So I can do an example of that one. Let's see. So let's say for number 1, I had y equaled x over x squared minus 1. Here in the numerator, my degree is 1, and in the denominator, my degree is 2. So by rule number 1, if the degree of the numerator is smaller than the degree of the denominator, this means that we'll have a horizontal asymptote at y equals 0. That one's easy, right? Okay. Rule number 2. If the degree of the numerator is equal to the degree of the denominator, then the line given by y equals a sub n over b sub n is the horizontal asymptote. So what this says is that if the degree of the numerator equals the degree of the denominator, then your horizontal asymptote is the leading coefficients of the numerator over the denominator. So for an example for that one, let's say I had y equaled 2x squared over 3x squared plus 1. Here, my degree in the numerator is 2. My degree in the denominator is 2. The degrees are equal. Therefore, by rule number 2, what would my horizontal asymptote be? Anybody? Tough crowd today. So if my degrees are equal, then it's the leading coefficients over each other. So for this example, what would my horizontal asymptote be?
2/3.
That's it. Y equals 2/3. All right. Okay. So rule 1 and rule 2 are nice. Rule 3 is the ugly one. Rule 3 says if the numerator is bigger than the denominator, then we no longer have horizontal asymptotes. So if the numerator is bigger by 1, then we have an oblique or linear asymptote. And the only way to find this linear oblique asymptote is by long division. And once you use long division, your quotient would be in the form of y equals mx plus b. So for an example with that one, let's say I had y equaled x cubed plus 1 over x squared minus 1. In this example, my numerator is bigger by 1. So this means we no longer have a horizontal asymptote. We would have an oblique asymptote. And we would have to find by long division, which I won't do for this one because I have examples down below. All right. And then rule number 4. It's a fun rule. I don't even know if it's a rule. I probably made it up. So rule number 4 says if your numerator is bigger than the denominator by 2, then you no longer have a horizontal or oblique asymptote. This asymptote will resemble a power function. So we can call it a power asymptote. And if this happens, then your power asymptote is going to be the leading coefficients over one another, and you will subtract the degree of the numerator from the degree of the denominator. So for rule number 4, let's say I had y equaled 2x to the 4th minus 1 over 4x squared plus 2. In this example, the degree of the numerator is 4 and the degree of the denominator is 2. So my degree of the numerator is bigger than the denominator by 2. So this means that you would get a power asymptote and you would put the leading coefficients over one another. So 2 over 4. And then you would subtract the exponents. So 4 minus 2. And my power asymptote, or my asymptote that would resemble a power function, would be 1/2 x squared. Okay. Those are the 4 rules for horizontal, oblique, and power asymptotes. Rules number 1 and 2, actually 1, 2, and 4 are nice. 3, not so nice. 3 requires long division. All right. Let's see. Cool. All right. You want something to do, Carl?
Yeah, send me the link.
There you go. All right.
Took me a second to find my unmute button. I was like, he's gonna think I don't want to work.
Yeah. It's okay if you don't want to. Nobody else wants to today, other than Pete. There you go. Boom.
All right. And this one is whenever it loads. Oh, it's hanging. It's thinking. It's
Boy.
taking a second.
It's Monday, man. It's Monday.
Yeah, even the computer's slow.
Yep.
This is 5.3 properties. Make sure this is the one that says 2021. This is the one we've been working on today, so it works out. Double check that real quick. I think it is. No, it's not. This is one you've worked out before.
So if it says 2021, you should see some writing, but not all.
Here we go. I got it. All right.
Okay.
Share my screen real quick. Okay. All right. Okay. All right. That's a little thick. How's that? That's good. Okay, so if we take a look at this, we have, remember the form that we're looking for here is a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot dot dot, right, over b sub m x to the m and so on, right? So we're looking for this first set of terms here, right, which correspond to this one and this one. So if we take a look at it, another color, I want to work with purple. We've got n will equal 3, m equals 5. So n is less than m, which tells us that we follow rule number 1, horizontal asymptote at y equals 0. And you're done. It's that simple. All right. You want me to do the next one too?
Why not? You got it.
Okay. All right. Yeah. So again, we're looking at our leading terms here. And to make this a little bit more explicit, even so compared to last time, we have 3x to the 4th, and we have x cubed. So this gives us that n equals 4. This gives us that m equals 3. We have n is greater than 3, so we have to follow rule number 2. And this one tells us that we will have an oblique asymptote at a line we have to find using long division of polynomials. So let's go ahead and do that on the side over here. A cubed minus, or x cubed minus x squared plus 1 is our divisor, and our dividend is 3x to the 4th plus 0x cubed minus x squared plus 0x plus 0. All right, so I'll do our first one, 3x to the
That's
4th.
supposed to be rule number 3.
What's that?
That's supposed to be rule number 3. If n is greater than m.
Oh, you're right. Yeah, you're right. My bad. That is rule number 3. My bad. Thank you for catching that. At least someone's paying attention. So this is equal to 3x cubed. So then we'll take 3. Just kidding. This is a cube. This is equal to just 3x. So we'll take that and multiply it by the divisor. And this gives us 3x to the 4th minus 3x cubed plus 3x. All right. So go ahead and write our answer up top. Or our first one, we had 3x. It goes right there. Do our math. Minus 3x to the 4th minus 3x cubed plus 3x. All right, so bring everything down. This becomes 0, right? 3x to the 4th minus 3x to the 4th. 0 minus a negative plus 3x cubed minus x squared plus 3x, right? Okay, so then let's go ahead and do our next one, and we'll get 3x cubed divided by just x cubed. And this gives us 3. Take 3 and multiply it by the divisor again. And we get 3x cubed minus 3x squared plus 3. Same deal, minus 3x cubed minus 3x squared plus 3. And we get 0. This is plus minus negative plus 3x minus x squared gives us 2x squared plus 3x minus 3. Don't want to forget to put my result up here, plus 3. Now, since we're at the end, we already know that this is going to stop, but just in case you overwork and get excited sometimes, I'll show you what happens, right? So our next one is 2x squared. We'll divide that by our x cubed, and now we get 2 over x. This means done. So the end result that we want, because this is what we care about here, is that we will have an oblique asymptote at the line y equals 3x plus 3. All right. Any questions on any of that stuff so far? Sounds like a no.
Number 3 is
Keep
the
going?
worst. Yeah, why not? You can finish
All
the
right.
next page.
Okay. All right. So let's take a look again. We look at our leading terms of our polynomials, and we have 8x squared gives us that n equals 2. We have 4x squared gives us that m equals 2. So this is n equals m. I think this one is rule 2. Let's go check. This one is indeed rule 2. All right. So we follow rule number 2. Now, remember, we are operating on this kind of form. And now what we care about is this part of it, right? Because rule number 2 tells us this. We will have a line at y equals a over n divide b, or a sub n divide b sub m. So these are what we're looking for, right? So what we get from that then is that our a sub n in this case will equal 8, and our b sub m will equal 4. 8 over 4 equals 2. So we have a horizontal asymptote at y equals 2. All right. And the last one, we've got, again, I'll always want to check, make sure you're looking at the right parts. We've got that 2x to the 5th gives us n equals 5, and x cubed gives us m equals 3. Something I should go back up here and note real quick on this one, right? On the n greater than m, we have that n is equal to m plus 1, and that's how we know that it's rule number 2. So if we look here, 3, yeah. When we look here, when n is greater than or equal to m plus 2, right? We have that n is equals m plus 2, right? So this means that we follow rule number 4, which tells us that we will have a, what was it, a power asymptote? It's a power asymptote.
Power asymptote.
And it's going to be at y equals, what was it? It was a over a n b m x n minus m, right?
Yeah.
Yeah, make sure that's right. I used to have these things memorized. It's been a while. So let's take a look at what we have here then. Let's just go ahead and pull this information out of what we're given, right? We have, let me get a different color here. Let's do green. Let's do lime green. Why not? We have that a sub n is, okay, that's why not. That is gross. We'll just go back to a dark green. A tree, what is a forest green? Yeah, that's a happy little forest green. This is equal to 2. B sub m is equal to 1, right? And then we already have n and m. So from this, we can put all this stuff together and we'll get this. Y will be equal to 2 divided by 1 times x raised to the 5 minus 3 power. So then y is equal to 2x squared. And this is our power asymptote. All right. Any questions on any of that stuff? All right. That sounds like a no to me. Wait, this is not. Oh, this is just the graphing it part. You want me to do this part too? Or you want to do that part?
I could do this one. Let's get.
All right.
I'll jump back in. Tag in. Share. Boom. Boom. This is the
Do
last
something
one.
too.
Yeah, I got to do something too. All right. So we are given the graph of a rational function, and we are asked to find domain, range, intercepts, vertical, horizontal, oblique, or power asymptotes, if any of this given graph. So let's go ahead and start by the domain. Remember, domain deals with your x values. So looking at this function, what would our domain be?
Not 3.
It would, there's a break at 3. So that means that where would we start for our x values?
Infinity.
Negative infinity, we'd stop at
3.
3, and then union, start back up where?
3 to infinity.
3 to infinity. Good. And then what is my range?
Two.
We have a break at
Mm-hmm.
2. So where do we start?
Negative infinity.
Negative infinity, stop at
2.
2, begin again at
2 to infinity.
2 to infinity. All right. And then what is the only intercept you see here?
0.
0, 0, right? So that can even be a y-intercept as well. So 0, 0. Okay. And then, well, if there is a break at 3 in our domain, that means what is my vertical asymptote?
X equals 3.
X equals 3. And if there's a break at 2 in my range, what is my horizontal asymptote? Y equals what? 2. Good. All right. And that's it. There's no oblique or power asymptotes. So that's it. All right. So those are the properties of rational functions. We have asymptotes, we have multiplicities, and we have our rules for horizontal, oblique, and power asymptotes. So that is it for 5.3.